Imagine an autonomous vehicle. Its code is flawless, and its processors are firing with perfect mathematical precision. But then, a sudden, chaotic flash of light from the sun hits the camera lens, and the car freezes. For decades, automotive engineering operated on a straightforward premise. If the internal hardware doesn't break and the software doesn't crash, the car is safe. This is the domain of traditional functional safety. But self-driving cars face an entirely different problem. The external world is inherently messy and entirely indifferent to clean code. A perfectly functioning sensor can still be blinded by fog, confused by a rainstorm, or tricked by an optical illusion. This vulnerability is why the ISO 21448 framework, better known as SOTIF, was created. SOTIF stands for the Safety of the Intended Functionality. Its mission is to categorize and eliminate environmental variables. SOTIF systematically identifies unknown dangers, tests how the vehicle reacts, and turns those uncertainties into strict, documented safety protocols. SOTIF functions as a rigorous filtering process. It takes the unpredictable nature of reality and subjects it to continuous validation, reducing residual risk until the vehicle's behavior becomes statistically acceptable and predictable. To understand how an autonomous vehicle survives all this chaos, it helps to look at the machine the same way we look at a living organism. Clause 10.3 of the SOTIF standard evaluates the sensing systems, the eyes. True machine vision requires sensors that can pierce through blinding glare or heavy snowfalls without losing the shape of the road. Engineers inject simulated noise to find when vision fails. The system then relies on Clause 10.4, the brain. Recognizing garbled static, it recalculates, triggering a minimum risk condition, or MRC. It chooses a safe fallback, like pulling over and stopping. This is how a machine demonstrates reasoning under pressure. It realizes it can no longer see the environment clearly, so it mirrors the instinct of a rational human driver and opts for caution. Flawless cameras and radars are useless if the cognitive system isn't explicitly programmed to prioritize survival over the destination when confronted with the unknown. Every brilliant decision the brain makes must eventually become a physical action. That brings us to Clause 10.5, the actuation systems, the steering columns and braking mechanisms that serve as the machine's limbs. These limbs must execute digital commands in fractions of a second, fighting against heavy physical burdens like the shifting weight of a fully loaded passenger cabin or the sudden loss of friction on an icy slope. However, assembling perfect individual parts, eyes, brain, and limbs, does not guarantee a functional organism. That requires Clause 10.6, the integrated system test. When you place highly sensitive digital components inside a physical, moving chassis, mundane design choices can accidentally cripple the AI. Something as simple as the chemical makeup of metallic bumper paint can weaken a radar signal, or the specific curvature of a windshield might refract a forward-facing camera's view of a pedestrian. SOTIF strictly mandates that engineers hunt down these exact physical conflicts, ensuring that hardware placement doesn't quietly sabotage the software's capabilities. An autonomous system only survives the real world when its digital intelligence and its rigid physical limitations are perfectly harmonized. The focus of all this technical validation eventually leaves the laboratory and enters the passenger cabin. At this stage, Clause 10 moves beyond the simple checkmarks of corporate compliance and controlled laboratory metrics. It provides a massive, documented body of evidence that the machine can handle a chaotic world, proving through thousands of stress tests that the vehicle's responses are no longer a matter of luck. This transition from blind hope to verified performance builds the foundation for the architecture of trust. Because engineers use SOTIF to actively map out and neutralize the unknown, we can finally achieve the ultimate goal of autonomous travel: safely letting go and believing in the machine.